Thank you. Thanks for all of you who have showed up here and for the few who are online. Hopefully everyone can hear me online. If you want to interrupt me, feel free to do so at any time. But I'm mostly going to be looking at the audience who's actually here in person. Okay, so the problem actually is quite simple. The forecasts that we see left, right, and center, weather, sports, and so on. And the question is, on what basis can we compare them? Okay, so I'll formalize this as we go along. This is joint work with YJ, who is a student in the stats department or the StatML program. And this was like for a course project that I'll talk about from last semester, and he is the lead author. Okay, so here's going to be like a running example to keep in mind. These are actual forecasts made on, there was a Nationals versus somebody else. This was in the finals of the Major League Baseball last 7 games. And you can see that, so these are actual, the World Series, exactly, the World Series. Clearly, I'm a cricket fan and not a baseball fan. So the World Series, so 538 has, a set of predictions that it made. It makes these before each game. So before game 1, it said 38% for Nationals winning. And then VegasOdds.com is a website, the sports betting website. There are prices there. It's actually easy to convert prices into implied odds. We won't get into that for the moment, but essentially the price at which you can buy or sell, against or for the Nationals can be translated into an implied probability. And so for simplicity, now just think there are 2 different forecasters, Nate Silver producing some set of probabilities, and then VegasOdds.com producing another set of probabilities, and then there's an actual set of outcomes. And you can see in this particular example, they're not very good. I don't know, they're okay. Like both of them said 38 and 35%, and for the first game, but the Nationals did win. They improved it to 41 and 38%, but still thought they would lose, and the Nationals did win. Then they actually took opposite sides for game 3, like, a little bit on the opposite side at least, like 538 was a little bit more towards Nationals winning, and then Nationals lost. Okay, and then so on and so forth. And you can see that for the last game, again, they were on the wrong side, but at least 538 was less on the wrong side in some sense, and they won. Okay, so now they're producing some sequence of numbers, and then you see some sequence of outcomes. And for this talk, I'm going to keep it simple, that it's just binary outcomes and 1 step ahead forecast, which means that I don't forecast all 7 games at the very start. I just forecast before each game. And so in the paper, we have extensions to lots of other settings, but for simplicity, this is going to be the setting. Okay. Hopefully that's better. And then, yeah, if it's not, mention in the chat and so on. So I didn't say anything great just yet, except for this discussion, except for just telling you what the problem is. And so the question that we're going to ask in this talk is, is one of the forecasters statistically significantly better than the other? And so, for that, we have to, the most important part of it is like trying to understand what does it even mean for one to be statistically significant. That's going to be the majority of the talk. It's actually going to be fairly philosophical and mathematical in the second half, but philosophical in the first half. Okay, so here's going to be the game protocol to think about. Okay, so there's a context XT that is revealed for event T. And so you can think about this as which teams are playing, any injuries. So like it's just some arbitrary context, it doesn't really matter. It's not going to play a role, but think about there being some side information available. And now there's like 2 forecasts that are going to be made simultaneously. So let's say there's 2 players, P and Q, and they make forecasts PT and QT, both in the 0-1 range, 0 probabilistic forecasts. They're made by these 2 players. Then after that, the outcome is revealed, 0-1, which happens. And actually, it turns out that a lot of this, what I said above is actually inessential. I'm just stating a game because it just helps make things concrete. But it actually turns out that none of these details are going to matter too much. So for example, XT could be different for the 2 players. One of them could have better measurements of the weather, or one of them could have insider information from the teams about the mood. It's not really going to matter what XT is. The forecasts need not be made simultaneously. Maybe player one goes first, and then player two looks at player one and then makes a forecast. That's also fine. And then YP may not be revealed to both players. Maybe one of the players finds out the answer, but the other one maybe finds it out after some time. So you can imagine other settings. It's all of these things are really not going to matter, but we need to fix things. So this is the game protocol that I'm going to ask you to think about for the rest of the talk. And you'll see that everything that we say will apply to all of these alternate game protocols. Okay. So one standard way to compare forecasters is to use the scoring rule. So let me tell you what a scoring rule is if you haven't seen it before. So it's a function of two things: the prediction and the outcome. And so it's just S of py. It's a bivariate function. One nice example would be the Breyer score. So this is from whether it's called the Breyer score. We might just call it the squared loss or something like that. But it's p minus y the whole squared. I've just put a negation so that higher scores are better. Otherwise, if it was without the negation, then a higher score would be worse, because let's say you predict 1 and the outcome is 0. That's the highest, p minus y the whole square is highest. So the negation is just there so that higher is better. But it's not really critical. We could have worked with lower being better. Then we would have called it a Breyer loss maybe, or something like that. Okay, so that's what a scoring rule is, just some way of saying, well, here's your prediction, here's the outcome. That's that's how well you did. And it has some historical roots in honest forecast elicitation. Okay, so here's the setting to imagine like what motivated the development of scoring rules. So imagine that we reward forecasters based on how well they did. For example, we might reward them a dollar amount that's equal to their score, or basically, since the score is negative, you can say it's that score plus 1, just so that you're rewarding them an actual positive amount. So now that, imagine that there's a forecaster that in their head thinks that, I think it's 60-40 for tomorrow's game. That's what they actually think, or for tomorrow's weather or whatever it is. That's what they think. You can ask, how do I incentivize the forecaster to tell me the truth? And the answer is, if you use a scoring rule like the one above, Breyer score, then if they want to maximize their expected reward, then they will actually tell you what they think. They will tell you that true belief B, what they think is the other probabilities. There's no incentive to game the system. And so, formally, mathematically, what that means is, this a scoring rule, a bivariate function like this, it's called strictly proper, or the strict part is if there's only one maximizer for this optimization problem, but it's proper if this thing holds. So I'll just help you parse it. S of py is the score that, that's the amount of dollar money they get, or 1 plus that. The 1 plus doesn't matter for the optimization problem, but that's the amount of money they get. This expected amount, that's according to them, according to what they believe, which is it's Bernoulli B, according to their own belief, this is their expected reward. If they say P and the outcome happens to be Y, that's their expected reward. And you can ask, what value of P, which is what they report, what value of P maximizes their expected reward if they think that the truth is B? And the answer is actually, it is B itself. If you say, if they report anything other than B, they will actually get a lower expected reward. So that's a simple thing to check for yourself that it holds. But essentially, this says that if a forecaster wants to maximize their expected reward, then they will report the truth. So this is where the roots come from of this. I'm not going to need the roots. And in fact, like for this talk, I'm not going to assume that I'm going to not assume that they are honest forecasters or anything of that kind. But I'm going to use Breyer scores because scoring rules are very popular in forecasting to compare forecasters, okay, or to evaluate forecasters, to encourage forecasters to tell the truth. Scoring rules are very popular, so I'm going to use scoring rules. There's nothing special about the Breyer score particularly, so that's one example that I'll use as a running example. But there's many other proper scoring rules. So like here's a few others. There's one called the 0-1 score. It gives you basically, if you predict it in the right direction, then it gives you 0 or 1 based on whether you predict in the right direction. That's a 0-1 score. That's proper, but not strictly proper. Strictly proper meaning that only B maximizes maximizes that expected reward. If it's proper, if B and other things could all maximize their expected reward. So in this case, the 0-1 score is ambivalent to where you predict above 0.5. So if you believe the truth is 0.6, you could say 0.7, you could say 0.65, you'll get the same reward. So it's proper, but not strictly proper. Then there's other ones like the spherical score, the log score. So there's all kinds of rules. I'm not going to, there's like thousands of rules. But for simplicity, let's go with the Breyer score because it's easy to think about.
Sorry.
Yeah.
So the Breyer score, that's a specific S function.
Yeah.
It has the proper property.
Strictly proper, actually.
Proper.
Yeah.
Okay. And all the other ones?
They're also proper. There are also other examples of proper scoring rules.
How hard is it to prove like the Breyer is?
Very easy. One line. It's like essentially like the.
You didn't put that line in the slide.
Yeah, I didn't put that line. Yeah.
What does Berr mean?
Oh, Bernoulli. Oh, that's a good question.
Sorry.
Yeah, so it's like, since I'm dealing in this talk with binary events, and it's like saying if Y is drawn from a Bernoulli B, if I think that it's a Bernoulli with 60% probability, what should I actually tell you? Should I say 60 or should I say 65? And it turns out that if you want to maximize your expected reward, you'll actually just tell me the truth. You'll tell me 60. That's the motivation behind the scoring rules. But in some sense, for us, the motivation is going to matter less. We're not going to assume that these forecasters are honest. They could be doing whatever. They might be non-rational and lying. I don't know. They're making some set of forecasts. We will evaluate them using some scoring rule because that's kind of standard in the forecasting literature. Okay. So one natural way in which you might want to compare the forecasters, you choose a scoring rule like the Breyer score, is to look at how well what's the difference in their Breyer scores, how well they're doing. So you can look at the empirical difference due to game T, and that's just S of PTYT minus S of QTYT. So those are the two different forecasters making it, and we compare to the actual outcome. So the hat there is because it's the empirical difference. I can actually calculate this quantity using the data that's available to me, which are the forecasts and the outcomes. I can calculate this. That's what the hat is signifying. That's it. And then you can average this. And this is just for a single game. That's the difference, the score differential. And so on. You can average that over T steps, and that's the capital delta. So the little delta is one game, and the capital delta is averaged over the games. Okay, so that seems like a natural metric to use. And this is what we intuitively in our heads say when one forecaster says 43% and the other one says 38%, and it happens to be a 0. We'll say, you know what, in this round, 38% was better. That's what we intuitively say, is where we're looking at some kind of a score differential and saying, 38 was closer to Y, P was closer to Y than Q. Or if it was a 1, then we might say the other way around. But the point is we're effectively looking at something of this kind intuitively. Okay, but now the question is, this is just an empirical difference. It's going to be non-zero. At any point in time, it's going to be non-zero. And unless P and Q say exactly the same thing in every round, it's going to be non-zero. So, if you see that after 5 games, delta hat 5 is 0.28, that's the difference currently. It's larger than 0. Q can simply claim that this just happened by chance. There was a sequence of outcomes. We both made predictions. There's a sequence of outcomes. P got lucky. And so we need some way of quantifying chance, of saying, this isn't attributable to chance in any way. Q is actually significantly better than P, or whatever. P is significantly better than Q. So we don't have that yet. We're going to get there, but this is the problem. So currently, this is a standard way to compare forecasters, but now the question is, how do we differentiate? We look at a number, how do we know that's not just chance? So to do that, we're going to look at an amended game protocol. Okay, so this is a second game protocol. It's going to look very similar to the first one, except there's going to be a new player that enters the game, and that's called reality. Okay, so as before, context XT is revealed, and these forecasts are made by both players. But now we we imagine this is totally imaginary and such a thing doesn't exist in reality. But let's say that there's another player called reality that chooses RT in 0, 1. And this is not revealed to anybody. It's not revealed to the data scientist looking at the data. It's not revealed to the players. This is just hypothetical and it's in our minds. Reality chooses RT and this is not revealed to anyone. Imagine that the outcome YT was generated according to Bernoulli RT, and that's what is revealed to both players. Both players only see YT, and this reality is just entirely fictional in the middle. Okay. So now, the interesting thing about this protocol, like now we have introduced this reality in the middle, is that what you're going to see the rest of the talk, we will make no assumptions about PT, QT, and RT. Okay, so we have no idea how the forecasters are coming up with their forecasts. We're not going to assume stationarity, IID, mixing, nothing, no assumption on how they come in. But most importantly, this protocol only makes sense because we're not going to make assumptions about reality. We're just going to throw in this player reality, but we're not going to make any assumptions about that sequence. When I put a bracket, I just mean the sequence and not just one. So the entire sequence of RTs, we're not going to make any assumptions. And the analysis, the actual final comparison between the forecasters will only be based on the observables, which are PT, QT, and YT, not RT. So there's going to be nothing in the final statements of comparisons that depends in any way on unobservables like RT, and no assumptions will be made on the unobservables like RT. So, so that should be okay. Yeah. It could be. So it could be. So that is an allowable, as I've just now written over here. A lot of the above could be inessential in the sense that that's the stuff I said before, like the players need not play simultaneously, all of that. And now the additional inessential part is it's like really RT could be anything. So it could be oblivious, it could be adaptive, it could be deterministic. You can imagine RT equal to YT in every round. That's an allowable RT. It could be stochastic, it could be anything. So we're not going to make any assumptions on that sequence. And so what you said, RT could be YT, that's allowed in this protocol. RT could be YT. So yeah, that's right. So RT could be just 0 or 1 in each round. So maybe reality just says RT is 0 in this round, and that's what you see. And then the next round, reality says RT is 1 in this round, and that's what you see. That's possible. That is a possible sequence of plays by reality that's allowed. But we're also going to allow reality to do other things potentially, and we're not going to restrict reality in any way. So that's a particular instantiation of reality. Okay. So I think the key part, which we will come back to repeatedly, is we will make no assumptions about RT. Okay, that what that sequence is. It could be YT.
Are you going to now analyze RT as a potential player? Compare RT to the other players?
No. We're not going to do that. But for now, we have just introduced another player, and we'll see soon why we have introduced that player. But we're not going to. It's not going to then.
Some other player.
No, reality is this new player that we've introduced. Yeah, but when. Yeah, they're another player, but we're not going to compare RT to PT and QT. RT is just a hypothetical God or nature or something like that. We're just making that a little bit more explicit. That's it. Okay, so why does introducing RT help? Okay, so now RT helps because we can now define some kind of a target quantity. We can say, I don't know what reality is doing up there. Maybe reality is adversarial. Maybe reality is stochastic. I don't know what reality is doing up there. But what I should be trying to compare the two players on is in the score differential of PT with RT and QT with RT. I don't know what RT is. So I don't know what delta T is. And I don't know what capital delta T is. I don't know what these quantities are. But these quantities are at least now non-stochastic in the sense that maybe delta hat T might change, on different realizations, or if the coin came up differently or so on. But little delta T and capital delta T, they don't change. They're well defined in this larger hypothetical game. They're well defined objects. So what we really want to do is we want to do something like, if delta T is greater than 0, we want to say that P has been better than Q on average, up to game T. And of course, the problem is we don't know RT, we made it up. We don't know delta T, we don't know capital delta T. So we don't know these things, but what we would like to say is not something based on delta hat t. We don't want to say something based on delta hat t. That could have been there could be some chance in there, but delta t is something that is maybe a well-defined target. Okay, so how do we get around this fact that we don't know any of these quantities, but we would like to reason about them? Okay, so here's a little break to tell you about confidence sequences. Okay, so this target delta t, it's an unknown parameter that we would like to know. Is it greater than 0? Is it less than 0? We'd like to know. And what we're going to do is we're going to produce a confidence sequence for delta t. But to produce a confidence sequence, I have to tell you what a confidence sequence is. Now, hopefully everybody knows what a confidence interval is. Confidence interval and a confidence sequence is simply a sequential analog of a confidence interval. Okay, so here's the definition. A confidence sequence for a parameter theta that you don't know. It's a sequence of confidence intervals, LTUT, L for lower, U for upper, and T indexes that they're constructed from the first T samples. And they have a uniform or simultaneous coverage guarantee. And so what I mean by this uniform or simultaneous coverage guarantee is that the probability that for all t from 1 to infinity, theta lies in this LTUT. So this is a good event, meaning my interval actually covers this unknown parameter. The probability that that happens simultaneously over all time is at least 1 minus alpha. Okay, and so the fact that the for all is inside the probability is what makes it simultaneous or uniform. This was, this notion was introduced by Robbins. That's the first photograph, Robbins, in the late 60s. And then others like Lai and Siegmund and others worked with Robbins in the 70s to develop this notion. And it's much stronger than what you've been taught as a confidence interval. A confidence interval has only a fixed sample size guarantee, which means you fix n beforehand, and the for all n is outside the probability. So you say, I'm going to compare them at time 1000 only. And then you look at the probability that theta is contained in the 1000th confidence interval. That has to be at least 1 minus alpha. So there's a very big difference between these two. So here's an example for a coin. So like, forget the forecasting example for a second. Let's say that I give you a coin and I allow you to toss that coin and I want you to estimate the coin's bias. Okay, this is a very simple problem. -1 is heads, +1 is tails. In this example, let's say it's a fair coin, so the true mean is 0. So you flip it, you see heads, heads, tails, tails, heads, tails, and so on. And the black dotted line is the empirical mean of your observation so far. Okay, it's not going to be exactly 0, but if you look far enough to the right by the law of large numbers, it'll tend to 0. And now what I'm showing you are two different objects. The green dotted line is the pointwise confidence interval. You can get that from a binomial theorem or a central limit theorem or something of that kind that says that I think that's where the true mean lies. And what you're seeing in the pink line is an anytime confidence interval, or that's what a confidence sequence is. So confidence sequence is, you should think about it as a band over all time. So the green dotted line is only valid at a fixed time if you fix the time beforehand. You cannot continuously monitor the green dotted line. And so here's a nice example at time 140. You can see that the confidence interval does not contain 0. So if you were really tracking the coin over time, you could stop at time 140 and say, oh, the confidence interval for the bias of the coin doesn't contain 0. I am confident that it is biased upwards, biased towards heads, and you would be wrong. And that's because confidence intervals are not valid under continuous monitoring. But confidence sequence is valid under continuous monitoring, and they're usually about square root log t wider than the confidence interval. So that's by the law of the iterated logarithm. And you can see that in the first number of coin, the tosses is small, like 40 or something like that. There's quite a big difference, but by the time it's 100 or 150, there's actually a very small difference. It's like a small expansion of the confidence interval gives you a confidence sequence, but this band has the guarantee that the band will always contain the true mean, in this case 0, simultaneously from 1 to infinity. Okay, so I've not told you how I constructed that band, but that's what a confidence sequence is. It has the guarantee that it will always contain 0 from time 1 to infinity. And here's a different way of writing the same guarantee. Now, earlier I wrote a coverage statement. Now I'm writing a miscoverage statement. It's like an infinite union bound. It says that the probability that at some time theta does not lie in my set is at most alpha. So that's that I ever make a mistake is at most alpha. So some implications of of this kind of a guarantee is that it allows for valid inference at stopping times. So for arbitrary stopping times, tau, or stopping time is you look at the data and you choose to stop adaptively. The probability that theta is not in L tau, U tau is at most alpha. This is not true for a confidence interval. Confidence interval, you have to fix the sample size ahead of time. You cannot just go see, check as you go along. You can't do that. It also allows post hoc inference in hindsight. So, you can look back at past times, which are random data dependent times, and you cannot violate the validity. And essentially, the main use of these things is that you don't have to pre-specify a sample size ahead of time. You can extend experiments adaptively. You can stop experiments early. So as you're going along with tossing your coin, you can toss for however long you want to toss, and when you're happy, you can stop, and what the interval you report will be correct nevertheless. Okay, so that's the utility of these.
You said in the previous slide with the graph that the sequence confidence interval, confidence sequences will always contain 0.
With high probability, with probability 1 minus alpha.
Oh, that's why I was
Yeah.
asking about that, because there's an alpha here.
Yeah, that's right. So
it's with high probability.
Yeah.
It's not
over the whole sequence, right? So if I do this experiment million times, which is I toss an infinite sequence of coin tosses, in 95% of those experiments, the confidence sequence will contain 0. But yeah, so basically on the previous slide, it is with 95% probability, 0 will lie in the band from 1 to infinity. It'll always lie in that whole infinite band. That's shrinking. As you can see, the band is shrinking to 0 width. Okay, so we would like, in this case, a confidence sequence for delta t, which is this quantity we don't know, and we're not going to make assumptions about, but we would like it. Okay, and so if we could achieve it, it would allow for continuous monitoring. As the games are played between these teams, you can continuously monitor the data. You can keep peeking at what the confidence intervals are. You can stop comparing them and award a trophy to one of them if you want. That would be an adaptive data dependent stopping time at which one is proclaimed to be better than the other. You can do all of that, and your inferences would not be invalid. It's all non-asymptotic, which means that it's valid in finite samples. It doesn't require the number of forecasts and events to go to infinity or anything of that kind. What we're going to do is we're going to make them distribution free, which means that I should not make any distributional assumptions, IID, stationary, anything on the forecasts, PTQT, or on the events like RT. I'm not going to make any assumptions about those. That's going to be the key part, distribution free. And I would like it if they're sharp or tight. And this is what on the previous slide, it should shrink to 0 width. Like it should not be too loose. It should ideally shrink in width as more and more data is observed. So essentially your ability to compare the forecasters should get better and better and better with time. So that's reasonable. We would like these things. So what we're going to shift, like earlier we said, if delta t is greater than 0, we would like to proclaim one as better than the other, but we don't know delta t, we don't have access to it. Instead, we're going to construct a confidence sequence, LT and UT, based on the data. And then what we can then say is, well, if the lower bound is above 0, then we can confidently proclaim. How confident depends on the level alpha you choose. Think of alpha as 1% or something of that kind. And then we would be able to confidently proclaim that P has actually been better than Q on average up till game T. Okay, and essentially the way of thinking about that probability, that statement, how quite confident, is that if LT is, let's say alpha is 0.01 and LT is above 0, and P says, or we say P is better than Q, and Q says, oh no, that could have just happened by chance. What this statement is really saying, because it's distribution free, is there is no reality that you can imagine, such that we can attribute it to chance. There's no reality. Reality could have been adversarial, it could have been stochastic, it could have been adaptive, it could have been oblivious. There's no reality that you can possibly imagine such that we can just say, oh, this happened because of chance, at least. And so it's going to be the fact that it's distribution free gives a very strong statement that Q cannot simply attribute P's performance to chance, because what we're going to say is we're going to construct a confidence sequence that's valid for any sequence of RTs. Okay, so we'll see how to do that. Okay, so now the question is, how do we construct this confidence sequence that's distribution free? Yeah.
Yeah. So on this like distribution free meaning. So like I'm trying to put it in my head of like the example you said earlier. So does this mean like if Nate Silver like every day like looked at the Vegas odds like before, and like knew your scoring metric, knew your alpha, and was like trying to optimize it to give himself the highest chance of being statistically significant? If he still is, then he actually is. Is that the advantage of this? Or am
Yeah. So that's right. We'll come back to Nate Silver versus Vegas odds, but yeah, essentially, like the two players could have been making their forecast, however, meaning actually P could have been making it based on Q's forecast, Q could have been making it based on. In fact, for example, VegasOdds.com, like it's possible that some of the people betting on their website were looking at Nate Silver's predictions. I don't care. Like, I mean, the thing is, okay, if they make exactly the same predictions in every round, then they are identical. But if they make different predictions in every round and then we see the outcomes, the question is, can we compare them? And the answer is, we can compare them based on the empirical observed score difference, but not just based on the empirical one. We're going to give a confidence sequence for that, for the true underlying score differential. And essentially what that confidence sequence is it accounts for all possible stochasticities that you could possibly come up with to potentially explain, you can suppose Nate Silver says, oh, well, actually, the score differential was near zero. Well, if it was near zero, the probability that you see something that's strictly, far away from zero is going to be negligible, meaning at most alpha. So
if they know your score.
Yeah, exactly right. Yeah.
Okay, cool. Thank you. That makes sense.
Yeah, and we might as well just fix the scoring rule to be prior score. So just think of the scoring rule as prior score. They know they're being evaluated on prior score. That's fine. Okay, so there's several related works, and maybe I should return to these later on, but essentially DF is distribution free. And there's many works on this in the past comparing forecasters, but they're usually not distribution free. They'll assume some kind of stationarity of the events or some kind of mixing or a Lindenberg condition, things of that kind. NA stands for non-asymptotic, which means that some of the past works required the number of events to go to infinity to be able to compare them. So they're asymptotic comparison of forecasters, but we don't want that. Maybe I have no idea how many events are going to happen and whether these two forecasters are going to keep forecasting or not. So I want something non-asymptotic. ST is it valid at stopping times, or do you have to fix the number of comparisons ahead of time and then look at it at that once, or can you adaptively go along? And so essentially, our method satisfies all of these properties. So does a very recent other method, but ours is for estimation and theirs is for one-sided testing. And they test a very strong null. So a strong null is they test, like the hypothesis that they test is that P is better than Q in every round. And that's a very strong statement. Why would one be better than the other in every round? Instead, we're effectively testing a weak null, which says P is on average better than Q. I mean, so it's much more informative when you to test a weaker statement than a stronger statement. Those are subtleties. We could return to them later on, but maybe the takeaway message is that we achieve all of these properties, and that's going to be nice. Okay, so one key property that we're going to use of the Breyer score, it's not specific to the Breyer score, but that we're going to use is, it was introduced by Lai. This is the same Lai as Lai and Robbins, who introduced multi-arm bandits and so on, who studied multi-arm bandits in the 80s. And so Lai also looked at forecasting, and he introduced this idea of a linear equivalent. Okay, so a score like that's a quadratic score. Well, he said that quadratic score or some other score S, it has a linear equivalent S tilde if two things hold true. One is that S tilde is the linear function of R, and S minus S tilde doesn't depend on P. Okay, so these are two properties. It might look a little weird, but here is the linearized Breyer score. So S tilde plays the role of a linear equivalent to S, which means, as you can see, it is linear in R. And if you actually look at S minus S tilde, the P squared term cancels out, the PR term cancels out. So, those are the properties you'll see here. But, for scores that are linear in R already, you can just pick S tilde equal to S. So like the 0-1 score, the spherical score, the log score, the other scores that I defined on the earlier slide, they're already linear in R. And so you just S tilde, you can just pick as S, and then S tilde minus S is 0, so it doesn't depend on P, and S tilde is a linear function of R. So I'm writing the Breyer score as an example because S tilde is actually different from S in this case, so it's nice to see. So why do you care? Why does anyone care that a score has a linear equivalent? Well, here is the magical property. Okay. If S has a linear equivalent S tilde, then for any RT, the expected value of delta hat T given the past. So delta hat T is an unbiased estimate of delta T. Remember, delta hat T was the difference in scores, which is S of PT YT minus S of QT YT. That's what delta hat T is. Delta T is the thing we don't know. It's S of PT RT minus S of QT RT. I don't know what that is because I don't know what reality is doing. I have no idea. I made it up. But no matter what reality is doing, no matter what it could be doing, hypothetically, even if I hypothesize a reality, no matter what it could be doing, delta hat T is an unbiased estimator of delta T. And that's basically because of the, well, both of those two properties. Okay, so why is that nice? It's nice because no matter what RT, PT, and QT are, delta hat T, the sum of delta hat T minus delta T is a martingale. And for those who don't know what a martingale is, it basically is this statement. Delta hat T minus delta T, if I put delta T on the other side, that's the increment in this sum. The increment in the sum is mean zero. So it's a sum of mean zero increments. That's a random walk, basically. And that's what a martingale is. It's a sum of mean zero increments. Okay, and the nice thing is it's a martingale for any reality you hypothesize, and no matter what PT and QT these forecasters make. Okay, so it's a martingale in all of those cases. Okay. Yeah.
What's not clear to me is whether Lai worked this all out before you guys, or he just defined.
He defined the linear equivalent.
So he didn't use it for this purpose at all.
He didn't use it for. Actually, he did. After this, he went into asymptotics. So like after he realized that this thing is a martingale, he said, oh, I can define an asymptotic he used something called the martingale central limit theorem to define an asymptotic confidence interval for these quantities and so on.
He also defined the RRT concept as well.
No, he didn't define it explicitly. So he has some kind of a Lindenberg condition in there. And so it's not in this game theoretic setting. It's a little bit more of a statistical setting. So it's like the language used is different. It's like, but you can back read out if you translate his statistical setup to this game theoretic setup with players, then yeah, he is implicitly working with RT, PT, QT, but then he goes into asymptotics instead and uses conditions on that sequence of increments. And we're going to not go to asymptotics and not use any conditions on that sequence of increments. So that's going to be a difference. But yeah, he definitely realized that this property is very useful. The property that delta hat, no matter what reality is doing in some sense, delta hat is an unbiased estimator of delta T. Okay, so we have a martingale. So that's going to be nice because martingales are nice objects. But by themselves, martingales are not nice objects. So that's just what I said on the previous slide. But if the score function is bounded, which, like for example, the Breyer score is bounded, the 0-1 loss is bounded. Like if these score functions are bounded, for example, by 1, in the case of the Breyer score, then we can control the growth of this martingale. So how does martingale behave? The problem is it's a sum of mean zero increments. But if these mean zero increments could be absurdly large, then actually we can't say much about how it's going to behave. But if it's bounded increments, then we can control its growth. So how do we control its growth? So I've written a bunch of papers on this topic. Here's 2 of them. The first author was Steve Howard, who was a PhD student at Berkeley, where I was doing my postdoc. These papers appeared recently, but they've been on archive for a few years. And the way we do it is we design non-negative super martingales. Okay, so the martingale property that I wrote on the top, that's not good enough. It's not enough to control like the deviations and tell me how this thing is behaving. But if I go to a non-negative super martingale, that's enough. And so it turns out that if you have a bounded score function, then this process is a non-negative super martingale. So non-negative just means it's non-negative. It's an exponential of something, so it's non-negative. Super martingale is where the increments are less than equal to 0. Instead of being a martingale, it has mean 0 increments, and a super martingale, it has mean less than equal to 0 increments. And so it turns out that for any lambda in the reals, and in this case for any RT, PT, and QT, this process here is a non-negative super martingale. Now, if you've seen Chernoff bounds in your class, I'm assuming everybody nowadays in stats, ML, CS sees Chernoff bounds. This is a restatement, actually a stronger statement actually than the usual MGF bound for bounded random variables. So the usual MGF bound is that the expected value of the exponential of lambda times a sum of bounded random variables is at most exponential of lambda squared t by 2. So that's the usual MGF bound. All I'm doing is taking the right-hand side into the left-hand side. And what you actually get from that is that this process is a super martingale. So this is, you can say it's a restatement, or actually it's a stronger statement than saying, this is telling you something about the whole process, what it's really doing. It's a super martingale. Here's a different one that is not taught in class. It's not taught because it's very new. It's in those papers and things like that. I call it the empirical Bernstein super martingale. And you'll see that the first part of it is similar. The process that I'm trying to control is similar. The second part is very different, but it's not that different. So the two parts that changed are lambda square by 2 became this funky thing, minus log of 1 minus lambda. But it turns out by a Taylor expansion when lambda is close to 0, that behaves like lambda square by 2. So if you want to squint, I would just treat this as basically lambda square by 2. Okay. And the second term, instead of being t, is actually an empirical variance. So essentially what happens with Hoeffding is it bounds the deviations of this by the worst case deviations, which are achieved by a Bernoulli minus 1, 1, and that's where that t comes from, the worst case. But in this you get something which depends on the empirical deviations of that process itself. And so it's called an empirical variance term. So you don't have to really stare at it that much, but essentially this looks a lot like the earlier process, except it's called self-normalized, meaning that the deviations of the process are normalized by the process itself, and so this is called intrinsic time as opposed to real time. So that's another name for this process. Empirical variance, intrinsic time, things like that. So it turns out that this is also a non-negative super martingale for any RT, PT, and QT. Here you have to restrict lambda's range a little bit because of the log.
Why is it called a super martingale? It's negative, so it should be a sub-martingale.
No, this process is a super martingale, which means that if I take its expectation at t steps, I take its expectation conditioned on t minus 1 steps, then it's going to be smaller than it was at the t minus 1 step.
What Danny is saying is that it should be sub-martingale.
Oh yeah, this is a historical error. Like people regret it, but it goes back to Doob. They later on realized, if it goes down, why is it called super? I fully agree, and it confused me when I started too. And there are interviews with Doob and others who say they regret the naming that they came up with back then, but we're stuck with it. Super martingales go down in expectation.
Okay. Joe Doob?
Yeah, Joe Doob. Yeah.
So if we know like Azuma, so do we need to understand this stuff?
Yeah, what you get out of it is stronger than Azuma Hoeffding.
If I know like Friedman I found,
It's stronger than Friedman's inequality. What you get out of it is strictly stronger than Friedman's inequality. Yeah.
Maybe I'll ask final question. If I just know those, then this is too much for me to grok online.
If you know those, the problem is that like even Friedman's inequality is tight only up to some fixed time n, and what we really want is it to be tight simultaneously through all of time.
So if I believe a stopping type version of Friedman, should I just imagine that this is a stopping type version of Azuma or Friedman?
Yeah, it's a time uniform version of Azuma or Friedman. It's for all time from 1 to infinity. If I want to make a statement for time, and I want it to actually be reasonably tight from 1 to infinity, not tight at one time and not at other times and things like that, then it's so basically what you get is time uniform versions of Friedman or Azuma, but it's close.
So maybe I'm imagining in my mind that I'm just using a sort of using a Azuma bound.
Yeah.
But it holds for all three, not just for.
Exactly. Yep. Yep. Yeah. So for now, I've only defined the property of the process, and I'll tell you on the next slide how to use this property. So we'll see how to use this property. So there's this thing called Wheel's inequality, which I think is magical, and everybody should know what it is. So I've just in hazy, I've put what you saw on the previous slide. That log term I've just summarized by psi of lambda. The empirical term I've just called VT. Okay, so that's basically what you saw on the previous slide. So now what Wheel's inequality says is it's a time uniform version of Markov's inequality. So everyone knows what Markov's inequality is. It applies for non-negative random variables. Wheel's inequality is a time uniform version of Markov's that applies to, instead of non-negative random variables, it applies to non-negative super martingales. Okay, and it says if you have some process MT that is upper bounded by a non-negative super martingale, or it is a non-negative super martingale, then the probability that MT ever exceeds 1 over alpha is at most alpha. Okay, and so mathematically, when you translate that into our setting, you get for any PT, QT, and RT, the probability, which is only taken over the randomness in RT, that there exists any time at which our process KT exceeds 1 over alpha is at most alpha. And I should just point out that if I drop this exists, that's Markov's inequality. KT is a non-negative random variable. Its expectation is at most 1, meaning at time 0, when there's nothing that's just defined to be 1, but its expectation is at most 1. And this statement is what Markov's inequality gives you. Wheel's inequality says not only is it true at a fixed time, it's actually true at every time from 1 to infinity simultaneously. Okay, so that's a very powerful statement. And so here's what you get. You get out of this a confidence sequence in 2 steps. Okay, so the first step is like take this process KT that I wrote above. KT is centered at the truth that I don't know. So I don't know delta T. So instead, just define KT of D to be centered at D, okay, or T times D. So in here, what you should think of as T times D is replacing the sum of delta T. Okay, so that's now a process. I can plug in any D and I get a different process. And this earlier claim is that if you plugged in delta T, which you don't know, if you happened to plug in delta T, then you get a super martingale. But if you plug in things that are not delta T, you get something else. You get sub martingales, you get martingales, you get other stuff. You get stuff that has no property maybe. But if you plugged in delta T over here, capital delta T, you plug that in over here, you get exactly this earlier process. That's a non-negative super martingale. Okay, so that's good. So now what we can do is, I know that KT of delta T being a super martingale, it cannot exceed 1 over alpha. With high probability, it will never exceed 1 over alpha. So let me keep the set of all Ds such that KT of D is less than 1 over alpha. And I know that delta T must be in this set, because if I plug in delta T, that's a super martingale. It does not exceed 1 over alpha with high probability. Okay, so this set over here contains delta T with probability 1 minus alpha simultaneously over all times from 1 to infinity. It always contains 1. I can construct it at each step and it always contains that. Now, this might look tedious, but it's not, because I can just take log on both sides and move things around. And what you get effectively is that the confidence set that you get looks like delta hat T, which is what that first term is. And then plus or minus, some empirical variance divided by square root T. Okay, so that's the form of, actually I'm dropping a log T term here, but essentially what you get is it has that form, and you get it simply by, you have this KT of D less than 1 over alpha, you take log on both sides, you move things to one side, and then you get this. So this is the confidence set that you finally get out of this. And the idea is that no matter what RT is, no matter what you hypothesize reality to be behaving like, this will contain delta T with high probability over all of time. It will contain delta T. Okay, so we have achieved our goal. No assumptions on PT, QT, and RT. We have produced something that's fully data dependent that contains delta T over all time. No, it's actually empirical variance times log T. So basically, a confidence interval shrinks at a 1 over square root T rate. Sequence shrinks at a square root log T over T rate. That's the price you pay for going from an interval to a confidence sequence. Okay, so here is what you get on the actual real data. So there's 2 things to note before we actually go through the slides. Is that when you look at a series of 6 or 7 games, it's really impossible to tell 2 forecasters apart. They're forecasting almost the same quantity. Their difference in Brier scores is absolutely tiny. It's very attributable to chance. So instead, we look at every MLB game from 2010 to 2019. Look at what 538 predicted, look at what Vegas odds predicted. This is regular and postseason put together. These are like, whatever, thousands of games and, or almost 10,000 games. And what you see, this is the confidence interval, confidence sequence that you get. So I'm going to ignore two of them. There's various methods. There's a Hoeffding confidence sequence. There's the empirical Bernstein confidence sequence. We'll just look at the empirical Bernstein one. So that's this one, and solid blue is the empirical Bernstein one. And what you can see is essentially they're basically identical. Like you can't read. There's nothing really to tell them apart. Turns out that the final confidence interval is not the final one. There's no final one. It keeps going on. But at the right end of this plot, at the end of 2019, that confidence interval looks like minus 0.03 to minus 0.01. So, it appears that Vegas is marginally better than 538. It isn't really about this plot. Like, that's not what the story was about anyway. Maybe this is an interesting finding that, the market matches or beats the expert. That's interesting, that you can actually look at the odds from betting markets and that those are informative about the real world. That's nice. But other than that, this is not really trying to make a statement about those two. It's in fact, like in the paper, we compare other pairs. So you can imagine other forecasters, like a Nationals fan who always predicts the Nationals will win, and then these very quickly beat that, these kind of baseline ones. There's ones that just predict based on past performance, which is they have been winning at this rate so far. That's what I'll predict on the next round. And so 530 and Vegas both beat these kind of trivial. We have lots of baseline forecasters which are not informative and doing something trivial. And in that case, both 538 and Vegas are significantly better than those those kind of baseline ones. But when you compare them to each other, there's not much difference over a very, very long period of time. Yeah.
I guess to go back to something you said a while back, assuming that the bar score is bounding, which is why
Yeah.
What happens with the log score?
Yeah, we don't know what to do with the log score. The problem with the log score is that one jump could shoot you to plus or minus infinity. And like you could be like doing really, 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 really well, and then you're like at plus or minus infinity. So like now, unless you restrict the forecasters to predict between 0.01 and 0.99, and if you restrict them, then you can handle the log score. Then the log score is also bounded and you can handle it. But if you really allow the forecasters to say anything they want, they could get scores of plus or minus infinity, and we don't know what to do there. So there's a large class of scores, including spherical 0-1, Winkler score, Breyer, things like that, for which this stuff works, but doesn't work for the log score.
Say something in terms of the scores that were actually output by the predictors.
Yeah, I agree, maybe, but we don't know yet how to do that. Yeah, it's a good question.
Can I ask you?
Yeah.
So just trying to interpret what you just said, and you were comparing the Vegas.
Yeah, in this case, it's 538 and Vegas. That's what I'm plotting here. It's the 95% confidence sequence for delta T between 538 and Vegas. Remember, delta T is this hypothetical reality that I don't know. And it basically this width, what you should interpret the width to be is all possible attributions to stochasticity you could possibly come up with. Consider any possible set of realities, adversarial, adaptive, oblivious, anything. And that width says, you know what, this is how much I can attribute to chance. Even like in the craziest hypothetical reality you could come up with, it's included in there.
So that doesn't contain zero.
Yeah, in this case, it doesn't at the end. As you can see, most of it does. So they're pretty much doing similarly. And it's just that at the end, you can't really see what's going on over there. So I'm telling you that it actually doesn't contain zero.
Yeah.
I mean, you can take what you want from it. Like, it's not really to look at it and say, oh, so this is better. But it more gives you a framework for making such comparisons. And
You were going to tell me it was a 95% confidence interval? Or...
It is, yeah. The final 95% confidence interval is this. So Vegas appears marginally, because this is less than zero, Vegas appears to be marginally better. So this is meaning, on average, when you average the score differentials between over the first 10,000 steps, Vegas appears to be marginally better. And you can't, yeah, that's right.
Wait, so this time independent thing, does that mean like, okay, like come back in like 5 years and you take all MLB games from 2010 to 2024 or something, is the confidence interval guaranteed to be
in that?
No, because this is covering delta t, which is a time varying parameter. So it could be that in the first 10 years, Vegas is better, but it could flip. So, Vegas odds could get worse. And then, so in which case this will actually, move to go above zero. And then, it could be that later on Nate Silver is better. So it's just for whatever period you're interested in comparing them, you can compare them and you can keep extending this. See this plot, if you said, I want to keep extending it, you can keep extending it. That's fine. Yeah.
Where would the non-time dependent confidence sequence, this confidence interval, sorry, be on this confidence? I'm assuming it would be like a lot tighter.
Yeah, it would be a bit tighter. Not a lot. Yeah, it would be a bit tighter, but you couldn't track it ahead of time. You would just have to say, I'm going to compare them after 1,000 games, and then you're stuck with whatever you get.
So if you can compare the two, maybe you can try to hedge between the two and try to sort of get some kind of strategy which is trying to do as well as the better of the two.
Yeah, maybe. Yeah, that's possible. How to improve on two forecasters, how to combine forecasts. Yeah, different interesting topic. For now, I'm just asking, how do we compare two forecasters? And how do we say, this is not because of chance or something like that? The answer is hypothesize all possible realities you could possibly come up with and say, in all of the, even if you consider any possible reality, this process is a super martingale, and hence delta t, the quantity we're after, no matter what reality you come up with, delta t always lies somewhere here. It always lies inside this. So let me end with a couple of interpretations of Bayes inequality. What I told you is a mathematical statement, but there's actually a very interesting game theoretic interpretation of it. And it is that if you start out with $1 and you bet on outcomes that are, that the odds are fair or stacked against you, then your wealth in that game that you play ends up being a non-negative super martingale. And the probability that you ever get rich is small, which means starting from 1, the probability that you ever cross 1 over alpha is at most alpha. So turns out that Wheel came up with this stuff not using a mathematical language, but very much using a game theoretic language. And if you're interested in skip the summary briefly and say there's slides up. I taught this course last semester on game theoretic statistical inference, and there's plenty of slides and papers. So if this kind of thinking interests you, then at the intersection of game theory and statistics, then I'm happy to chat offline or take questions. But now that we're at time, I want to just thank all of you, and feedback is welcome. The paper is on archive, and thanks.
Concept of de-randomization. Suppose I want to get something higher probability. I'm not sure exactly what I want, but should I run 2 games in parallel so that all the odd games is one sequence, or the even games is one sequence? Compare the two. Maybe one case A does better, another case B does better.
Yeah, I don't know where de-randomization as a term comes up, because there's nothing randomized in the output. The actual confidence sequence output is fully deterministic. It just is the empirical delta hat t plus or minus some quantity. That's what you output at every step. So it's fully deterministic. The output is deterministic. But yeah, you could produce a confidence sequence for the even games separately and a confidence sequence for the odd games. I mean, you could, but I don't know a priori why one would hypothesize to do that. Like, you can't do that after looking at the data, but before looking at the data, you can say, this is what I want to do, and you could do that if you have some reason to believe it. But you should think about this as constructing the confidence sequence as you go along, even though I presented it to you in a way that the Major League Baseball games have already happened, and I'm doing a post hoc analysis of it as if we were running along with time. Because the forecasters were making their forecasts as if they were running along with time, we can do our analysis in this way. But you should think about it as, I can do this, I can construct this going forward. From today for the next 10 years, I can compare weather forecasters going forward, every day updating my forecast. In that case, I don't know why a priori I would think, let me compare them separately on odd days and even days. So I wouldn't know why one would do that, but you could stratify if you want to. You could say weekends and weekdays or something like that, or you could stratify as home games and away games. You could stratify, but there should be some reasoning behind it that you think that some forecaster might be better than the other. in that stratification. Otherwise, you're kind of wasting samples. You're halving your sample size, or something of that kind unnecessarily while trying to compare them. But yeah, you could, as long as you do it without looking at the data.